Let me introduce Wojciech Samotij. It's our pleasure to have him talk at our big seminar. Wojciech is an expert on probabilistic combinatorics and is very well known for his contributions and development of container methods, but his interests are much more broad. And today he'll talk about some Ramsey type results for random graphs.
Thank you very much, Andrei. Thank you very much for the invitation. So today I'll speak about threshold phenomena in random graphs with respect to Ramsey properties. And the content of the talk is based on, we'll advertise a joint work with Ehud Friedgut from the Weizmann Institute, Eden Cooperwasser, a young and promising graduate student from Tel Aviv University, and Matthias Schacht from Hamburg and Yale. So the title is A Sharp Threshold for Ramses Theorem, and I hope you accept my apology for starting the talk by stating Ramses Theorem. So Ramses Theorem says that if we color all edges of a sufficiently large complete graph with R colors, then if n is sufficiently large with respect to k and r, then we will always find a monochromatic copy of the complete graph with k vertices. Since saying every r coloring of the edges of Kn yields a monochromatic copy is a bit of a mouthful, it will be convenient for us to introduce the following brief notation. We'll say that G is Ramsey for H in r colors, or I will simply say G arrows H if for every coloring of the edges of now an arbitrary graph G with colors 1 through R, one of the color classes will contain a copy of the graph H. And a straightforward corollary of Ramsey's theorem, since every graph H can be embedded in a complete graph with the same number of vertices, Ramsey's theorem implies that if n is sufficiently large, then the complete graph with n vertices will arrow H in R colors. Now, in this talk, we're not going to speak about Ramsey numbers, but we're going to study at what densities the random graph, the binomial random graph GNP, has the property of being Ramsey for a fixed graph H in a given number of colors R. And so the main object of study will be this function mu of P, which depends on H, the graph H, and the number of vertices in the large graph, in the random graph N, and the number of colors R, but I will simply denote it by mu P. This is the probability that the random graph has the Ramsey property. So what can we say about this function? Here's some easy observations. When the edge density is 0, then the random graph is almost surely empty, and therefore it will never arrow H, so mu of 0 is equal to 0. Now, Gn1 is almost surely complete, and if n is sufficiently large, then this complete graph will have the Ramsey property with respect to H in R colors, and therefore mu of 1 is equal to 1. Now, two slightly less trivial facts is that the function mu is increasing, and this is because adding edges to a Ramsey graph keeps the Ramsey property, and there exists a natural coupling of random graphs at all densities, such that if P is at least P prime, if P is at most P prime, then GNP is contained in GNP prime. And another slightly less trivial property is that the function mu is continuous, and this is because any probability like this can be expressed as a polynomial entity. Okay, so if this function starts at 0 here and goes to 1 and it's increasing and continuous, there is a unique place which I call PC, the critical probability at which mu of PC is equal to a half. Now, a famous theorem of Bolobosh and Thomason states that there aren't too many sort of different shapes that this function mu can take for any monotone and non-trivial property such as being Ramsey. Namely, if I started PC and multiplied by some small constant, then mu of this PC times a small constant will be very close to 0, whereas if I multiply it by a large constant, then it will be very close to 1. In other words, there is some interval whose length is proportional to the critical probability, where the function mu makes most of its gain. It starts from at most epsilon, and it comes to at least 1 minus epsilon. In other words, we would say that this PC is a threshold for this property GNP. Namely, so if all the action happens at the order of magnitude PC. Now let me phrase this formally. So here's a definition. We'll say that the function p hat is a threshold for a graph property P. And here by a graph property, I will always mean not a property of graphs with a given number of vertices, but it will be a sequence of properties. We'll have some collection of graphs for every number of vertices. Now, a function p hat is a threshold if the probability that the random graph GNP belongs to the property converges to 1 if the density P is asymptotically bigger than the threshold P hat, or it tends to 0 when P is asymptotically smaller than P hat. What do I mean by asymptotically bigger? It means that the ratio of the probability to the threshold tends to infinity as n tends to infinity, asymptotically smaller, that this ratio tends to 0 as n tends to infinity. Now, the famous theorem of Bolobosh and Thomason states that every monotone, meaning preserved by adding edges, and non-trivial graph property has a threshold. A property is non-trivial if it's not satisfied by all graphs, but there exists a graph which satisfies it. And it is easy to check that the property of being Ramsey for H in any number of colors is both monotone, because adding edges cannot kill. If we add edges to a Ramsey graph, we will get a Ramsey graph. We just can color more edges, it's easier to find H. And also it's non-trivial because the empty graph clearly doesn't have it. But by Ramsey's theorem, if I take a large enough complete graph, then it will have the Ramsey property. So a natural question suggests itself. Bolobosh and Thomason say that this property has a threshold. And we may ask, where is this threshold located? What is the asymptotic value of this critical probability PC at which the probability of being Ramsey is equal to 1/2? This question was first asked in the early 90s by Wojciech, Ruciński, and Voigt. And the famous work of Rydl and Ruciński from 95 resolves this question completely. So what Rydl and Ruciński proved in a series of papers is that for every graph H and every number of colors, at least 2, there are 2 constants, C0 and C1, both positive, such that the probability that G and P is Ramsey for the graph H in our colors tends to 1 once P exceeds this function n2 minus 1 over the so-called 2 density of a graph H. So this is some parameter which depends only on the graph H. And if we multiply the same function by a small constant, if P is below it, then the probability tends to 0. So note that this is slightly stronger than saying that this function is a threshold for the Ramsey property, because we even show that we don't need to assume that P is asymptotically bigger than this function. It's enough if P is larger than this function by some multiplicative constant. And likewise for the 0 statement, we don't need P to be smaller than this function. We just need P to be at most some small constant times this function. And here, M2 of H is a number, a rational number, which depends only on the graph H. This is the so-called 2 density, the maximum over all subgraphs of the sum ratio of the number of edges and the number of vertices. Now, there is a small gray asterisk here next to this all, because as stated, this theorem is not true. There are several exceptions. So this theorem does not hold if the graph H is a forest of stars. So it's a forest whose every component is a star, or there's a very special case here, which I will say a bit more about later, is when H is a path with 3 edges and the number of colors is 2, then this part of the statement fails. The 0 statement here is not true. The 1 statement is true, but the 0 statement requires P to be asymptotically smaller than this function. And just to give credit where it's due, let me say that the special case where H is a triangle and R has 2 colors, which is already non-trivial, was solved earlier by Franklin and Riddle with a slightly, so this was the 1 statement with a slightly stronger assumption on P, and finally by Wojciech Samotij and Voigt in '92. These were the people who started systematic investigation of these kinds of questions. Now, this quantity 2 density, if you haven't seen it before, maybe it looks a bit mysterious. So let me explain some intuition behind the location of the threshold. Why is it n to the power -1 over this 2 density? So suppose that P is at the threshold. So it's some constant C, which we will play with, times this function, n2 -1 over n2 of H. And moreover, assume that F is some subgraph of H, which achieves the maximum in the definition of this quantity. So the number of edges of F-1 divided by the number of vertices -2 is equal to the maximum over all such quantities when F ranges over all subgraphs of H. Now, this quantity is defined in such a way that at this particular density, if we look at the expected number of copies of the graph F in G and P that contain a given edge, which is an edge of a random graph, then this expectation is of constant order. And moreover, this constant here will grow very large when we make C large, and it will become very, very small when this function C is small. This is because the number of edges here is at least 2. And let's denote the number of copies of F that contain E by NE of F. Now, if C is small, then for most edges, NE of F is 0. And the proof of the 0 statement is based on the following observation. If the number of copies of F on a given edge is at most R-1, where R is the number of colors, then one can extend any F-free R coloring to E. Namely, let's color everything outside of E. And now someone says, please color E. E is in at most R-1 copies of F. Perhaps each of them is almost monochromatic with a different color, but still there's a color which we haven't used because we have R colors, so we can always color E without introducing a monochromatic copy of F. Now for the 1 statement, however, making this rigorous, so it sounds easy because this way we can color, say, 99% of the edges, but coloring the final 1% of the edges, this is not easy. In fact, this is very difficult, and the fact that this theorem is not true in some special cases, like the path of length 3, shows you that you need to be careful. As for the 1 statement, I cannot give here any short explanation. Let me just say that if this constant C is large, then most edges are in many, many copies of every subgraph of H. And if you're interested in an accessible proof, there's a very nice short proof given recently by Rajko Nenadov and Angelika Steiger of the 1 statement of Ramsey's theorem, which uses the hypergraph container theorem. Now, what I really want to talk about in this talk, because as you see, this question is resolved, is the theorem of Riddle and Rucinski says if P is at least some constant times this function, then we're almost surely Ramsey. And if it's smaller than some constant C0 times this function, we're with probability tending to 0 Ramsey. Now, the question I want to ask is how close can I make the C0, the constant C0 and C1? And here a definition is in order. We will say that a function p hat is a sharp threshold for some graph property p if we have the following stronger requirement. So if my density p exceeds the threshold by just some multiplicative factors slightly larger than 1, then already I'm in the property, surely. And if I'm just slightly below the threshold, say 0.99, then the probability becomes already 0. So in other words, when you graph the function, then the jump from 0 to 1 happens at a window which is very, very small. It's of size little o of the value of the threshold. So if you want some physical analog here, a sharp threshold phenomena come from physics and they're observed in nature. Think of changing the temperature of water. Once the temperature of water crosses from plus to minus, then the properties really change. From liquid, it becomes ice. And this is the kind of behavior we want to study in much simpler models, such as coloring of random graphs. What are examples of properties which have a sharp threshold? Two famous examples are connectivity, the property that GNP is connected, and Hamiltonicity. Both of these properties have a sharp threshold, and the value of the threshold is log n over n. In fact, much stronger results are known here, but in this accuracy, this is the answer. An example of a property which has a coarse threshold is the containment of any fixed subgraph in GNP. For example, the property that GNP contains a triangle doesn't have a sharp threshold. It has a threshold because it's a monotone and non-trivial property. The threshold is at 1 over n, but it's not sharp. And the reason is that the number of triangles at any given density is roughly Poisson, and therefore the probability that we have no triangles is bounded away from both 0 and 1. When Ehud Friedgut started investigating these questions in the 90s, he observed the following, that every natural property he would come up with, which has a sharp threshold, is in some sense global. Like connectivity, we need all the vertices in the graph to be connected, or Hamiltonicity, we need the structure find structure in the graph which is spanning. And on the other hand, if a natural property has a coarse threshold, then it's in some sense local. So by local, I mean it only depends, or it's witnessed by a bounded number of edges appearing. So here we just need 3 edges to appear in the graph in order for this property to kick in. It turns out that this is not an accident. And what Ehud went on to prove is his famous theorem, his famous characterization of properties with coarse threshold. He proved that if a graph property has a coarse threshold, meaning non-sharp threshold, then it must correlate with the local property, with the property of containing a subgraph of bounded size. Now, I will state a more rigorous version of the theorem later, but this is a formal way of phrasing this intuition that properties that have a non-sharp threshold must be local in some sense. And in the context of Ramsey's theorem in the random graph, the following question suggests itself. Is the property that GNP is Ramsey for some h in our colors, is it a local property or is it a global property? Does it have a sharp threshold or a coarse threshold? This question was first investigated in 2000 in a paper of Ehud Friedgut and Michael Krivelevich. What they proved is a characterization of the sharpness of this property for every graph H, which is a tree, which doesn't contain cycles. What they found is that any star in any number of colors and a path of length 3 in 2 colors have coarse thresholds. Every other tree in every number of colors the threshold for the property G and P arrows T in R colors is sharp. And let me explain these two examples. So why is this threshold and this threshold, why are they not sharp? This is because if we want to guarantee that in every coloring we have a star with k leaves, it's enough that our graph will contain a star with k minus 1 times r plus 1 leaves. This is just by the pigeonhole principle. And such subgraph appears below the function, the density from the Rydl-Ruchinsky theorem. The situation with with the path of length 3 and 2 colors is slightly more subtle. The following graph, a 5-cycle with 5 pendant edges, is Ramsey for the path of length 3 in 2 colors, and it appears at exactly the Rydl-Ruchinsky density, which means that even if my probability is some epsilon over n, I have some very small but positive probability that this graph will appear, and then every coloring of this graph will have a path of length 3, and therefore the zero statement is not true unless my probability P is asymptotically smaller than 1 over n. And this is the reason why the threshold is not sharp. Now, this paper is about 20 pages long, and it proves also versions of this result where instead of coloring edges, we're coloring the vertices. The first result, which handled a graph which is not a forest, which contains a cycle, is a famous result of Friedgut, Rydl, Ruchinsky, and Tetali from 2006, who proved that the property that G and P is Ramsey for the triangle in 2 colors also has a sharp threshold. Why is this paper famous? Well, one of the reasons is that it's pretty long. It's 65 pages. It appeared in the memoirs of the IMS. It's a big technical challenge to prove this result. The same paper conjectures that, in fact, the property that G and P is Ramsey for H in R number of colors should have a threshold for any graph H which contains a cycle. For a long time, there was a little progress on this problem. And in fact, the only other known result is a recent paper of Matthias Schacht with his student Fabian Schulenburg from 2018, who proved that the threshold for the Ramsey property for H in 2 colors is sharp. If H satisfies the following 2 conditions, it's strictly 2 balanced, which means that the 2 density here in the maximum is achieved only for F equals H, and nearly bipartite, which means that H is either bipartite or it contains an edge whose deletion makes H bipartite. In particular, the triangle is nearly bipartite because it's an odd cycle. We remove an edge and we get a bipartite graph. And this is a generalization of the result of Friedgut, Rydl, Ruchinsky, and Tetali. Let me also mention an earlier paper of Ehud Friedgut and Hieb Han, Yuri Persson, and Matthias Schacht from 2015, which proved an analogous result in the setting of van der Waerden's theorem. So we're looking for a monochromatic arithmetic progression in a coloring of random set of integers. This paper, in fact, made a big leap compared to this work because it introduced new methods which significantly simplified the technical aspects of this earlier work. So this is cut down from 65 pages to 19 pages, something more manageable. However, one challenge remains.
Wojciech, can I ask you a question? So, so do you mean that this later result implies the Friedgut's theorem?
So the proofs of all these results use Friedgut's theorem, and I will explain later how. What I'm saying is that the theorem of FRRT the proof is 65 pages because there's a lot of technical things that need to be done. And this paper,
but is the last result implying the first result on this slide? This is what
the last result, no, but the theorem of Schacht and Schulenburg is implying the Friedgut-Rudolph paper. This is about 35 pages, so it's half of the length, but it proves something more general.
Okay.
For example, this proves that for every cycle, the threshold is sharp.
And can you also give an intuition why all these results assume R equals 2?
So this will become clear later.
Okay.
So this is what I want to highlight, that apart from the result about trees of Friedgut and Krivelevich, all the results for graphs that contain cycles work only in the setting where the number of colors is 2. And the result I want to talk about today is joint work with Ehud, Friedgut, Eden, Cooper-Wasser, and Matthias. So we're finishing writing it. What we proved that if H is a graph from a class that I will define only at the end of the talk, which includes all clicks and all cycles, then the threshold for the Ramsey property is sharp for every number of colors, at least 2. The class is defined as follows. We need our graphs to be strictly 2 balanced, but we also need them to have 2 extra properties, which I don't want to state now because they will naturally come up later, and now they will be taken completely out of context. So since in the remainder of this talk, I would like to give a proof outline for the theorem in the special case of the triangle and where the number of colors is 3, then maybe this would be a good time for questions. So maybe let me pause for a minute or two and see if anyone has any questions, and you're very welcome to ask.
So just on a general level, I guess you'll state it, but this theorem implies the theorem of Schacht and his student from the previous slide.
Yes, because these 2 extra properties, when the number of colors is 2 and the graph is almost bipartite, they are satisfied.
Mm-hmm. There is a question in the chat also. Do you compute the sharp threshold? So do you know the value of the sharp threshold?
Thanks. Very good question. No. So the way this result is proved is, so Ehud's theorem allows one to prove a sharp threshold result without knowing the precise location of the threshold. So the only information about the threshold we have is that it's between the 2 constants C0 and C1, which can be computed from the argument of Riddle and Rucinski. So in particular, it could be possible that the threshold is just oscillating between these C0 and C1. However, none of us believes that this is the case.
Mm-hmm. Wojciech, if you want, we can even take a small break for a couple of minutes if you need the pause. Otherwise, some speakers do that. It's up to you.
Okay, I think maybe the remainder of the talk will take about 40 minutes. I'm happy to continue.
Okay.
But also maybe if we do make a break of
a quick question.
Sure.
Is there a short proof of the Rudolph-Rucinski theorem using the Schacht method or containers or so, like they use for the arithmetic progressions or something?
So you mean just for the threshold result?
For triangles, yeah. 2 colors.
But the sharp threshold or just the threshold?
Just the threshold.
Just the Rudolph-Rucinski. So there's this paper of Rajko, Nenadov, and Angelica, but this is only the one statement. But the same paper has a proof of the 0 statement, which perhaps slightly simplifies the Riddle-Rucinski work, but it's still not easy. So proving the 0 statement, I can try to convince you that this cannot be very easy. One thing that you need to check is that the complete graph on 5 vertices has a coloring which is triangle free. I think we lost Dhruv. So answering Drew's question is that the proof of the zero statement just has some intrinsic difficulty that, in my opinion, prevents us from giving a really short proof of it.
There is one more question in the chat, Wojciech. I don't know if you see the chat.
Yes. So do I know of substantial family of pairs having a coarse threshold? So other than what is given here in the theorem of Ehud and Michael, so any star and a path of length 3 with 2 colors, I don't know of any such family. And I do believe that if we assume that H is connected, then these are the only 2 counterexamples. However, I wouldn't bet money on it, but my feeling is that this is true. And especially for 2 colors, I believe that this should be true. So let me perhaps continue. So in the remainder of the talk, I just want to give a proof outline for this theorem in the special case of the triangle and 3 colors, but I'll try to present it in such a way that at least in the end, I will highlight how the general proof goes in a final slide, because I will have some hopefully interesting open questions there. So maybe the bottom line here is that we have some family here, and the cliques are inside and cycles are inside, and there are some explicit conditions, but we already know that these conditions are not satisfied always. So one of these conditions is not satisfied always. So if you want to prove the statement for all graphs, then significant new ideas will be needed. Okay, so here's the setup. I will denote by mu of p the probability that G and P arrows the triangle in 3 colors. And as every such proof goes, I'm assuming that the threshold is coarse, and I will be seeking contradiction. So first, what does it mean that the threshold is coarse? It means that there's some interval whose size is whose length is proportional to the threshold, which for the triangle is 1 over square root of n, such that on this entire interval, the function mu p is bounded away from 0 and is bounded away from 1. If this is not true, then the threshold would be sharp. Now, in particular, there must be some p inside the interval where the derivative of the function mu is at most a constant over p. So where the probability is bounded away from 0 and 1, and the derivative is of order 1 over p. And this is, under these assumptions, I can now state what Friedgut's theorem implies. So Friedgut's theorem implies that there is this graph B of bounded size, which has the following property. If I start with G and P and add a uniform random copy of B, of a graph of fixed size, then the probability that I will be Ramsey for the triangle will jump by some small constant. So in other words, where I'm somewhere in between 0 and 1, and the derivative is bounded by 1 over p, then there is some local property, namely containing the graph B, which correlates with my Ramsey property. Adding a random copy of B will significantly boost the probability that we're Ramsey. So this is the probability that we're Ramsey without this extra copy of B. And moreover, somehow I'm not saying here anything surprising, because if I took B to be a large complete graph, then this probability would be increased to 1, and I'm not saying anything interesting. So there's a second condition which makes this theorem interesting, which says that B is a graph which has a positive chance of appearing at density P. So B is a graph that could appear here. And this probability is not 1, because if this probability was very close to 1, then we would already have the Ramsey property here. So it appears with some constant probability between 0 and 1. Now, usually in a proof of a sharp threshold result, one starts with the theorem of Friedgut and does some straightforward massaging to it. And the following corollary is a massaged version of Friedgut criterion, which this precise statement we'll be working with. So it says that there is some epsilon and the same graph B with a bounded number of edges that appears at this density with positive probability, such that if I take Z to be a sample from GNP, then with positive probability, with probability at least epsilon, I have the following two statements. On the one hand, if I start with my typical sample Z from GNP, then adding to it epsilon P extra edges increases the chance of being Ramsey by at most 1/2. On the other hand, if I add a random copy of B, then the probability that this will get me to the Ramsey property is at least epsilon. Note that the first item here, the probability that Z together with G and epsilon P is Ramsey is at most 1/2, means that Z itself is not Ramsey. So Z itself is not Ramsey, and adding to it extra epsilon P random edges, it doesn't necessarily give me the Ramsey property with probability at most 1/2. So sprinkling extra random edges gets me to the property with probability at most 1/2. However, adding just constant number of edges arranged in a nice way, in the form of a copy of a graph B, significantly boosts the probability that Z will now be Ramsey. Increases, it's at least epsilon, which is a constant. Now, how do we work with this? We'll prove that conditions A and B are in fact mutually exclusive, and this is how we'll get the contradiction. So the contradiction will come from the fact that we'll take the property B and prove that in fact it implies that this probability has to be very, very close to 1. It cannot, if a random copy of B increases the chance of being Ramsey by some constant, then it must be that if we sprinkle epsilon P random edges, then this will almost surely be Ramsey. And this will be the contradiction. Now, how do we achieve this? Let's fix a graph Z which satisfies both A and B. Now,
Wait, can I ask you a stupid question?
Sure.
So when you write conditioned on Z, what exactly do you mean by this? Here, like you fix a particular.
Yes. So this probability is a function of Z.
Mm-hmm. Yes.
So this conditional, I'm saying this conditional probability is at most 1/2, and this conditional probability is at least epsilon. So this conditional probability, the randomness comes from the choice of G and epsilon P, and here the randomness comes from the random copy of B.
Yeah, and then when you write with probability at least epsilon, it means that for epsilon proportion of choices of Z.
Of Z, yes.
Okay.
Yes. Now, what we will do is we fix just one Z that satisfies this property and this property. Since this holds for at least an epsilon proportion of all Zs, then we may ask Z to have some typical properties. So in particular, Z can avoid any bad event which holds in GNP with probability at less than epsilon. This is because we have some room to spare here. And again, let me repeat what I said before. The property A implies that Z itself is not Ramsey for the triangle. Because if Z was Ramsey for the triangle, then this conditional probability would have to be 1. So in particular, there must be a proper coloring of Z with colors, with our three colors, red, green, and blue, which by proper, I mean, it doesn't have a monochromatic triangle. So this is the setup. We have a Z which has a coloring which avoids triangles. However, if we add a random copy of our graph B, our magical graph B, then we have a chance, at least epsilon, that the union of these two graphs will be Ramsey for the triangle. And the next slide will introduce two crucial notions. The notion of availability and forcing of colors. Let's fix some coloring of Z with red, green, and blue. Now, if two edges are colored red, and I have some edge of Kn here, then if this edge would appear in my second random graph, Gn epsilon p, then for sure I cannot color with the color red because this would create a triangle. And therefore I will say that the color red is unavailable for this edge E. If this edge appears in the second stage of randomness, then I cannot color it red. Now, if both red and blue are unavailable for some edge, then the color green is forced. If this edge appears in the second round in Gn epsilon p, I will have to color it green. I have no other choice. And here's a crucial observation. If there is a triangle whose all three edges are forced to some color, then our coloring cannot be extended to this triangle. Because each of these edges I have to color, say, green, otherwise it forms a triangle with the earlier edges. But now since the three forced edges form a triangle, then we will have a green triangle if we color them green. And once the notions of forced edges are introduced, here's a proof outline. The proof will go as follows. We'll show that for every proper coloring of Z must force a positive proportion of the edges to some color. And second, it forces a positive proportion of all triangles to some color. This means that if this coloring can be extended after adding a second stage of randomness, then this random graph must avoid all of these triangles which are forced to some color. So we will bound this probability of avoidance of all the forced triangles of Gn epsilon p, and finally we'll take a union bound over all colorings. So our property A was that adding a second random graph with density epsilon p, still we have chance at least a half that will not be Ramsey, which means that one of the proper coloring of Z we must be able to extend it to this subgraph. So in particular, for one such coloring, this random graph must avoid all the forced triangles. There's n cubed of them by 0.1. And we will show that this is little of 1, and this will lead to a contradiction. So again, we'll show that every proper coloring forces a positive proportion of the triangles to some color. Now, the probability that Gn epsilon p avoids all of these forced triangles for a given coloring is very small. And then we'll take a union bound over all colorings, which will contradict the fact that with probability 1/2, we can extend some coloring.
Wojciech, and where do you use this second property from the massaged version of Friedgood's theorem?
The second property I will use to show that there are many forced edges.
Okay.
Right. So here's how I will use it. How will we show that there are many forced edges? Again, I'm sorry for hiding a proof by contradiction inside a proof by contradiction, but this is how I found it the easiest to explain. So suppose that only very few edges are forced. Now, if I take a uniform random copy of B, then the probability that it will contain some forced edge will be very small. Right? The expected number of forced edges is at most the number of edges of B times little of 1, but the number of edges of B is constant. So this probability is negligible. Now, as the triangle is strictly two-balanced, and the number of edges of Z is roughly n2 3/2, we're at the 2 density for the triangle, then a random copy of B also has very small chance to intersect the graph Z. We're adding a random copy of a graph with constant number of edges over a graph with small density. And more importantly, the only triangles in the union of Z and a random copy of B have 0, 1, or the maximum number of edges in the copy of B. So either they're completely contained in Z, or completely contained in B, or have one edge in B and the remaining edges in Z. So the probability that one of these two properties does not hold is little of 1 for a random copy of B. But we know that the proportion of copies of B whose addition to Z makes us Ramsey for the triangle is at least epsilon. Since the probability of having a forced edge is small, and the probability of failing one of these two properties is also small, then I must have a copy of B so that if I add it to Z, the graph becomes Ramsey for the triangle. Each edge is not forced, which means that it has at least 2 available colors. And the only triangles in the union are either completely in Z, completely in B, or have 2 edges of Z and 1 in B.
Wojciech, can you repeat this part? I'm a little bit lost, especially this. Where do you take this Z union phi of B has a triangle?
Okay, so
this part.
My property from Friedgut's theorem says that if I take a random copy of B and add it to Z, then with probability epsilon, it will arrow K3. But I don't want any copy here. I want my copy to satisfy some additional properties. And these 2 properties that I can guarantee is that the only triangles in Z union B are either completely contained in Z and they're already colored, or completely contained in B, or have 1 edge in B and 2 edges in Z. I cannot have 2 edges in B and 1 in Z. This is what I'm excluding. And I can guarantee it from the assumption that K3 is strictly two-balanced.
Mm-hmm.
And the fact that each edge has at least 2 available colors is because of our assumption that we made to reach a contradiction. So let's copy. If we assume this, then we have a copy of B which has the following 3 properties. Z together with the copy of B are Ramsey for the triangle. Each edge of B has at least 2 available colors, and the only triangles look like this. And here comes my key property number 1. The graph B, and every graph which has a positive chance of appearing at this density, is 2 choosable with respect to the triangles. Meaning, every edge here has at least 2 available colors. And from these available colors, I can choose a color for every edge so that no triangle in B is monochromatic. Now, what does it give me? I have now a coloring of this copy with no monochromatic triangles that uses only available colors. So no such triangle is monochromatic. no such triangle is monochromatic because Z is already colored. And also no such triangle is monochromatic because this color was available at this edge, meaning that I didn't have a copy of K12 in the color. So we didn't have monochromatic triangles that look like this. We didn't create any monochromatic triangles that look like this by the two choosability property. And because the color was, we only colored from available colors, none of such triangles is monochromatic. So the proper coloring of Z can now be extended to a coloring of Z union phi of B. And this contradicts our assumption that Z union F of B are the triangle. And so why is there a contradiction? Because we assume that only very few edges are forced. If we didn't assume it, then the copy of B, one of the edges would have some forced color, and therefore we couldn't use this key property number 1.
And this key property is just random coloring? Or how to prove it?
Excuse me?
How to prove this key property?
Yes, so in fact, proving the key property for any clique starting from K5 is very easy. Proving it for K4 is easy, and proving it for the triangle is somewhat more difficult. So in particular, even to prove that K5, the graph K5 is too choosable for the triangle, I don't know an easy proof of it. I mean, it's not very difficult, but there is some work to be done.
Mm-hmm.
Now, we have many forced edges. How to guarantee that we have many forced triangles? Now, this is, I'm not going to say much here. We know that many edges are forced to some color. However, in principle, they could form a triangle-free graph. Even if I had n squared over 5 forced edges, it could still form a triangle-free graph. In order to guarantee that this is not the case, we have the following key property number 2. Here's the property. If we have any partial coloring of the edges of Kn with colors red and blue, and it contains order n to the 4 graphs that look like this, meaning that this edge is forced to green, then it must also contain order n to the 9 graphs that look like this, which just say that this triangle is forced to green. So proving this for the triangle is not very difficult. Proving this for any bipartite graph is very easy because bipartite graphs have degenerate to run densities. So if we have n squared forced edges, then we need to have the maximum count of copies of the graph. However, this property, unfortunately, is not true for every graph. So this is a key requirement for our proof. It's true for the triangle, and it's true for every clique and every cycle, and every graph which is almost bipartite, but it's not true for every graph H. And key property 2 plus the property for edges with an application of the container lemma and a second moment implies the property T. And this is perhaps the most technical part of the proof, which I conveniently here summarize in one line. Okay, so maybe back to the plan. I told you a little bit about this and very little about that. Luckily, the next 2 steps are already very easy. What's the probability that G and epsilon P avoids a family of n-cubed triangles? This is just a standard application of Janssen's inequality. This is exponentially small in n squared P. So let's take a union bound overall colorings. we have the number of colorings times this probability, and now the number of colorings of Z is at most 3 to the number of edges, which is 3 to the n squared p over 2. And it seems like it doesn't work. Now, maybe we can get a better estimate on the probability, but definitely this probability can be lower bounded by the probability that this graph has no edges. It avoids an altered triangles, which is only exponentially small in epsilon n squared p. Now, the union bound over all colorings is too large. Well, it's a paper that we're still writing, so perhaps we can still fix the proof, but it seems that we won't be able to get away with just a simple union bound here. Luckily, there's a solution. It turns out that this union bound argument can be made much more efficient. We don't need to witness the entire coloring. It's enough to consider some partial colorings, which will describe the family of all possible colorings. So here's the key lemma that will allow us to complete the proof. We'll show that there's a family C of not so many partial colorings, exponentially many in little o of n squared p, which have the following property. First of all, every proper coloring extends one of our partial colorings. And still, even though it's only a partial coloring, it shares the property that it forces a positive proportion of the edges to some color. So we're able to show it for a proper coloring, but in fact, we're able to show it only for a partial coloring from our family. And in particular, it also forces omega n cubed triangles, because we show that every coloring that forces n squared edges forces n cubed triangles. Now, this union bound argument now works, because instead of bounding, in summing over all colorings, we now just sum over these partial colorings from the family C, which is only exponential little o of n squared p. So the final union bound is 0, 1. And these two conditions, with this condition, it just smells like an application of the container lemma. And in fact, the proof of this lemma is to apply the containers theorem for a hypergraph with this vertex set, which arises from the family of our boosters, of copies of our graph B with this property. So I don't want to say more about it. This is as much as I will say about the proof. I just want to finish with the following slide. So what I tried to present is some idea of how one proves the sharp threshold result for the triangle with 3 colors. Now, here are sufficient conditions for this threshold for a general graph H to be sharp. Property 1, sorry, the property 0 is that our graph is strictly 2 balanced. Property number 1 is that any graph whose density doesn't exceed the 2 density of H must be 2 choosable with respect to H from lists of colors from 1 to R. So this is why the case R equals 2 is especially easy, because 2 choosable from list 1, 2 just means 2 colorable. And such property was already established in the work of Riddle and Rucinski. So property number 1 was already verified in the 90s by Riddle and Rucinski if the number of colors was 2. And the final property was this complicated property about forced edges imply forced triangles. It means that in order to establish it, one needs to show that for every 1 up to R minus 1 coloring of Kn, if we see a full count of structures like this, an edge supporting an edge removed copy of H in every of the r-1 colors, then we must have a full count of copies of H so that every edge of it supports such monochromatic H minus an H. And this is very easy to check when H is nearly bipartite, somewhat more difficult when H is a clique, but unfortunately, this property is not true for every graph H. So if you would like to prove that this property has a sharp threshold for an arbitrary graph H, then some significantly new ideas, a twist on the approach would have to be found. And let me stop here. I think I've used enough of your patience, but I'll be happy to answer any questions.
Thanks a lot, Wojciech. You've been quicker than you anticipated. So I think we have a lot of time for questions if people want to ask some. Chilil, let me ask you something. So here, when you remove this edge, it means any edge, right? It's not the same edge.
Yes, I have no control over this edge.
Mm-hmm.
So it's for the clique or for the cycle, it doesn't matter because all edges are the same. But in general, I have, and also maybe an important remark in the proof of nearly bipartite, this E1 doesn't have to be the same as this E1. And this E1 could also depend on the pair UV.
Mm-hmm. And the main, as you said, the main simplification that comes from working with two colors is key property 1 only, or key property 2? It's
no, it's key also property 1 because this two choosability becomes a two colorability question. And the reason why it's easier is that the argument of Rudl and Ruchinsky that proves that such a graph is two colorable uses the fact that every graph with this density can be, the edge set can be decomposed into forests, into some number of forests. And then by coloring this forest, you say this forest gets colored red, this forest gets colored blue. You can construct a coloring which avoids H. And if you're dealing with two choosability already for three colors, then you don't know whether the necessary colors will be available, and you need to look for different arguments.
Okay, thanks. Any more questions?
I don't quite understand why two choosability appears here for arbitrary colors. So how do you define this? So in case of three colors, you
so in case of three, so why this two choosability appears, so I don't know if it's really essential in the problem, but this is something that came up naturally in our proof method. And I'm wondering, so someone asked me whether there are pairs of graphs, sorry, pairs H and R, graph and number of colors, for which the threshold is non-sharp. And I'm wondering now whether if there is a pair of graph and a color for which the two choosability property is not satisfied, does it imply that this property has a coarse threshold? If such a pair existed with R equals 2, then it does imply that this property has a coarse threshold. This is precisely the case with a path of length 3 and 2 colors, because the graph B was this 5 cycle with pendant edges. It was not two colorable. And I'm wondering now, say the number of colors is 3 and you are able to find such a graph B which is not two choosable from lists of size 3, does it imply that the threshold is coarse? Perhaps it does, but I don't know how to show it.
I guess one more thing is that you promised some open questions. I don't know if you will.
Yes. So the open question. There's no explicit open question here, but I hope that this final slide will point to the open question. So let me state them explicitly. Can you prove that threshold is sharp for any graph which is not strictly two balanced? Even a two balanced graph, and possibly the smallest two balanced graph would be this graph, K4 minus an edge, even in two colors. The second question, can you prove key property number 1 for all pairs H and R? So we know how to prove it for cliques and cycles, and I was working with one undergraduate student here in Tel Aviv University who proved it for some complete bipartite graphs. Is it true for every graph? And the most difficult question would be, suppose that a graph H doesn't satisfy this property, and I think the Peterson graph doesn't. The Peterson graph is strictly two balanced. Is the threshold for the Ramsey property for the Peterson graph, even in two colors, is it sharp or not?
Great, thanks a lot. Any more questions? Well, if not, then Wojciech, thanks a lot for your talk. It was very interesting. And we're looking forward to seeing this paper. By the way, do you have any estimate on when it should appear?
So I hope by the end of, so the plan is by the end of the year. All the mathematical part is inside already. We just need to polish it and write an introduction. So yeah, hopefully by the end of the year.
Okay.
Yeah. Thank you for the invitation, and thank you for listening. And I'm sorry if this second part of the talk was too much for, especially for the European time zones. Thanks a lot. Thanks, Andrzej. Большое спасибо.
Большое спасибо, Wojciech.